Now, if no question, then let's go to device physics, right? Again, I don't expect you to use a lot of math, but we still need to, sometimes we use intuition, sometimes you use math. At the end, I don't require you to memorize too many equations, but at least you should know the equation for capacitance. You should know the depletion width is inversely proportional to the doping, right? But you don't need to know the exact equation. And I uploaded a few pages of C. This is not the traditional C1. It's a easier to read one, right? So you can take a look. So first thing, let me talk about Fermi-Dirac function. Okay, Fermi-Dirac. So electron, when an electron, you know, it's quantum mechanics. So you always have to ask yourself, when you describe something, is quantum mechanics. So there's always some state. You cannot go into any energy level you want. There's a state. It's just like a house. You can live on 5th floor, 4th floor, and that bedroom, that particular unit, whatever, but you just cannot choose to live between the wall of 2 floors, right? It's not allowed, right? So we have state. So electron, they are so-called fermion. They cannot live in the same house, okay? Although sometimes we say, oh, you can have 2 electrons just because they have different spin. Spin itself is a state. You cannot have 2 electrons having the same state, right? And because of this, if you do some statistical analysis, you come up with this graph. Right? This is a very difficult derivation, so we are not going to derive it, and no need to derive it, but we need to appreciate it to have this figure in our mind. This is the house. It has different energy. Every level, I have a room, and I only welcome 1 electron to get in because it's so small. Pauli exclusion principle. So what is the probability of the electron to occupy certain energy? This is the building I've been talking about. 1st floor, 2nd floor, all the way to very top floor. This is the energy. What is the probability for electron to occupy? It generally follows something called Fermi-Dirac distribution, like this. Its probability is almost 1 when it is below certain level. And this level, we call it Fermi energy. Just take it for granted, right? Yeah, there's something called Fermi energy. If you are below this level, for example, this is the floor, right? Maybe you can imagine, maybe Fermi energy is the longest stair you have in this city. And you don't have stair in this house. So all you can do is that you can climb up to Fermi energy. Maybe not a good analogy, that may make you make other wrong conclusion. But basically, it's just saying that below Fermi energy, right, you have a probability to occupy there by 1. And above is very small. But and Fermi energy is defined as the probability is 0.5. Okay, so then we have the so-called Fermi-Dirac statistics. It say the probability equals to 1 over exponential energy minus Fermi energy divided by kT minus 1. Okay, a plus 1. Okay. You don't have to memorize this equation. If you can, that would be great. Right, we are going to talk about this later. We have 3 types of distribution, basically 2 types, Fermi-Dirac and Bose-Einstein. Bose-Einstein is for photons, spin integral particle. They can occupy the same place at the same time. Right? Fermi-Dirac is for those follow Pauli exclusion principle. Right? So that is the Fermi-Dirac distribution. It's talking about what is the probability to occupy the energy at different level. And usually depends on this constant Fermi energy. Fermi energy is a constant for different system. Or I cannot maybe even say constant, it can change Fermi level, right? But this is, for example, at temperature equal to 300 Kelvin. If I go to absolute zero, this is T equal to 0 Kelvin. So when temperature equal to 0, then you see that all of them must be below Fermi level, okay? I don't know how deep you are with this concept, but the point is you don't need to worry too much, but the point I want you to is have this insight. Higher temperature, more electron excite to higher energy. This makes sense, right? And then the Fermi energy tell you the probability the electron has half to occupy that level. Any questions? Is this clear? Right. So later, if you did not pay attention, you might think that I'm talking about T equal to OK, but this is T equal to 0 Kelvin, right? For example, this is T equal to 300 Kelvin. Then you won't get confused. Okay. Now, then let's go to band structure. What we are studying is this on the top. I have a silicon at the bottom, and then I have a silicon dioxide, and then I have a metal. Metal, the special thing about metal is that it doesn't have band gap. All the electrons are filled up to Fermi level, okay? It's possible you have some electron at high energy at room temperature, but if imagine this is just a 0 Kelvin, then it will just fill up to here. But that won't change our conclusion because what we care is about Fermi energy. You might have electron on the top, very few, but Fermi level is where your probability goes to 0.5. Okay, so you have a Fermi level for metal. Okay, this is the oxide. We're doing a vertical cut, right? So we see the metal first and then oxide. Oxide is pretty wide. It has a conduction band here, right? This is so-called conduction band. Valence band is down at the bottom. We don't see it because we don't care that much in here. Okay, and then here we have silicon. We have the conduction band here, valence band here, right? So in valence band, we have a lot of electrons. These are all electrons, right? But our Fermi level is at this level. Fermi level, I say that the chance you occupy here is 0.5. It doesn't mean you can, because this time we did not build any room between these two levels. This time the building is like this. Yeah, I have a lot of room, but then I don't want to build it. And this is the so-called band gap. Yeah, if there were room, yes, you have 0.5% to probability to occupy here, but sorry, there's no room. So you have this probability from statistics, but there's no room, of course, then you don't occupy. And that is the band gap, right? And now, what happened? Now, there's a few things we want to say. How do we draw this band diagram? Let's study a few things. Can someone tell me what is electron affinity? Maybe you forget, right? This is just Q chi. It's just the vacuum level. This is the vacuum level. If you don't know what is vacuum level, just think about Einstein's experiment, photoelectric. You want to shine a light to the metal, then the electron becomes energetic enough and leave the metal. If once it leaves metal and it go to the vacuum without kinetic energy, that is the level. It's just saying that how do I leave the semiconductor or how do I leave the metal? It is the energy that you need, I mean, not the energy. This is the destination when you leave the metal, and that is the vacuum level. So electron affinity is just equal to, let me call this E vacuum, right? It's just equal to E vacuum minus EC. So you see that electron affinity for the conduction band is different from the electron affinity. For the silicon is different from the electron affinity for the oxide. Some material have even negative electron affinity, which is diamond, passivated diamond. It means that if you put electron there, it will just leave. It will just inject because its energy is higher than the vacuum level. You just want to jump over the cliff. Okay, so this is electron affinity, right? What is band gap? Can someone tell me how do you calculate band gap?
It's energy difference between conduction and valence band.
Very good, thank you. I know maybe it's easy for you, but still hope that you can participate. EC minus EV. So band gap for the silicon is very small, 1.12 EV. For the oxide, it is about 9.1 EV. Wide, very wide, okay? And what is Fermi level? It depends, right? It can be not depends, it's just EF, constant throughout everywhere in this case, okay? And then now we say what is work function. Work function is very important. It is just the Q phi m, this one. It's just equal to the vacuum level, E vacuum minus EF of the metal. Okay, this is the work function for the metal. How about work function for the silicon? Q phi S equal to E vacuum minus EF of silicon. This one. Okay. Now, if just so these are some definition I require you to memorize. Okay. Now, what can I just look at the diagram? Is there any difference between insulator and between silicon and the oxide? I don't see any difference. It's just that one is larger, one is smaller. In principle, insulator is just semiconductor, except that it has very wide band gap. Since it's so wide, you don't have electron goes into the conduction band or hole in the valence band. Now let's review the Fermi statistic a little bit more. Just now we say that the Fermi statistic follow distribution, right? This is the energy, correct? And then you have this. Remember, here is the Fermi level. It gives you 0.5, right? So I do have some electron that can reach that high into the conduction band. But think about if the band gap is so large, the electron that can reach conduction band becomes less and less. That's why it becomes insulator. So oxide, of course, it is insulator, but it's just equal to very wide band gap semiconductor. There's no fundamental difference. Okay, of course sometimes they are not crystal, however, they're amorphous. But it's difficult to say, but I want to ask you to see in this way, right? Even it is a crystal, it is just a wide band gap semiconductor. Okay, now, and then two very important things I put in red. Fermi level should be constant when it's zero bias. It's not the conduction band. At zero bias, you can have band bending. Think about the PN junction, right? Maybe I'll cover in the later, yeah, right? Remember, for example, right? For example, think about this PN junction. I apply zero bias. You all know how to draw the band diagram for a PN junction. Is there a bending in the conduction band? There is, but it is zero bias. Why? Because this Fermi level is constant. It's all about constant. If you learn about chemistry, this is called chemical potential. Right? Last time we talked about drift and diffusion. Although you have an electric field there, but I also have a diffusion counteract it. The chemical potential are the same, right? So at zero bias, what is voltage? It's chemical potential. All our battery made from chemical reaction, right? So this is called chemical potential. This is called Fermi level, has to be constant. Then there's another thing called flat band condition. Flat band is what? Now it's talking about the band itself, nothing to do with the Fermi level. Here we're talking about the silicon substrate has to be flat, no bending, horizontal. Zero bias doesn't mean that it's flat band. Do you see this PN junction? I have zero bias, but it's not flat. Here it is flat, just a coincidence. That is a message, right? I want you to take. Many students, right, including myself, right? I keep reading, studying from undergraduate to grad school, even when I'm working. This is was still something confusing me until eventually I really can memorize. So you need to keep correcting yourself. This is a very important concept. Zero bias means constant Fermi level. If you don't understand why, memorize it. When you draw the diagram, you need this one, Venn diagram, right? Flat band condition doesn't mean that it's zero bias. It's just that we make it flat. You might need to apply certain voltage to make it flat. Okay? Any questions? Let's quickly just do one example, right? Now, for this diagram, what if I apply a negative bias to it? Maybe I don't do it because it's last minute. I think it will be confusing to you. Maybe can you let me know if you have any questions? Maybe it's better to answer some question. If no, I think we can stop here. And then we start the device physics. The most important thing is to understand this diagram, right? This is a band diagram cutting from the gate to the oxide to the P substrate, right? Can someone tell me which one is the Fermi level for the, which one is the work function or Fermi level for the metal, right? Fermi level is this one, right? Fermi level, EF. What is the work function of the metal in this diagram? Work function is to remove the electron from Fermi level to where?
Q phi m, Q phi sub m.
Very good. Yeah, is to remove the electron from the Fermi level to vacuum, right? That is the Fermi level. We also have the Fermi level for the silicon, Q phi s. Okay. How about affinity, electron affinity? Which one is the electron affinity for the semiconductor?
Q-chi.
Great, thank you. It is to remove the electron from the conduction band to the vacuum. Okay, how about the band gap? Which one is the band gap? I hope everyone knows this for silicon. How do you find band gap in this diagram? Band gap is from where to where?
Conduction band and valence band.
Thank you. From the conduction band to valence band, right? Okay, so I hope that you understand this. These are the basics, right? And then we talk about the Fermi-Dirac distribution on the right, right? So here we show that at different temperature, right, you have different probability. Usually you will see this graph, but last time I showed you this graph, I just rotate it and flip it. Why? Because this usually align with our band diagram, right? Because this is the energy vertically. So here's the vertical energy. And then this is the probability you will occupy. So 1 here is the Fermi level. When you're below Fermi level, at 0 temperature, right? Then you actually have all of them under Fermi level, right? And then you have very low probability to occupy the high energy, because for every point here, the probability is almost 0. When it is very hot, for example, the KT is equal to mu, which is the Fermi potential, then you see this one, right? But no matter what, at the Fermi potential, you always have 0.5 of probability to occupy. Okay, any question about this Fermi energy, Fermi-Dirac distribution? And this is the equation. Yeah, good to ask now, right? Any question, feel free to ask. Don't say, I just go back and study again. That will take you more time. Right? And you don't want to lose the point, right? The exam, because for something that you could have asked already. Okay.
I have a question. So this distribution, do we use, I remember there was an approximation, the Maxwell distribution. Do we approximate with that?
Very good. So he talked about another approximation. That one, we are going to talk about that later, but we can mention now. So this is the Fermi-Dirac distribution. Exponential E minus EF divided by KT minus 1 plus 1, right? What if your energy is much larger than EF? If E is much larger than EF, and you put into the exponential part, of course, exponential of E minus EF divided by KT is much larger than 1, right? Then this becomes what? Probability equal to 1 over exponential E minus EF divided by KT, which is exponential, this is 1 over, right? Negative E minus EF divided by KT. And this is so-called, let me write here, right? Boltzmann distribution. Or like what you say, Boltzmann-Maxwell, I guess, okay? So this actually is fitting this part. These are the high energy parts. If you try to plot with this function, you will see the same thing. So are we going to do that? Yes, because Fermi-Dirac distribution usually is not integratable, right? You usually need to use some, we call it Fermi-Dirac integral of order of half or whatever, right? But here it is easy to integrate. So when we integrate the electron, we are going to use this. So we will do that, right? But this is a good point. The point is that Fermi-Dirac distribution, if it is, you look at the high energy part, they are just the Boltzmann distribution. And this is the distribution you know very well. Higher energy, lower probability, right? Exponentially. Any questions? Make sense? Okay, let's move forward. I really hope that you can participate, because as I say, in this class, I want to have an atmosphere to immerse you in all the terminology. Every slide looks complicated, but if we keep talking about this, repeating, I hope that you understand by your heart. Right? That is the purpose of this class. And I want to